Over 140 million cars and trucks use the U.S. streets and highways. And over 10 million new vehicles are sold in the United States each year. The automobile service industry, the business you and we are in, is as healthy as ever. But the automobile itself has undergone continuing and dramatic changes during the last decade. And we in the automotive service industry have to keep up with those changes. Take a look at the vehicles of today, and what do you see? Oh, it's obvious there are more small passenger cars and trucks on the road now than ever before. Even the largest sedans are smaller than their predecessors of a few years ago. And the weight of the typical passenger car has shrunk from approximately 4,500 pounds to about 3,000 pounds, about 33%. But it's on the inside, hidden under the sheet metal of today's vehicles, that even more dramatic changes have taken place. Front-wheel drive, McPherson struts, four-wheel independent suspension, rack and pinion steering, adjustable rear suspension, electronic ride control, four-wheel steer. All of these are becoming normal features in today's cars. And these features have made a dramatic difference in the way vehicles are serviced and maintained, particularly in the way modern passenger cars should be aligned. Today, you need to know more about suspension systems and alignment than ever before. Over 70% of the new vehicles being manufactured and sold have suspension and steering systems that will need four-wheel alignment as opposed to an inadequate front-wheel alignment. Hunter Engineering, the foremost manufacturer of precision auto service equipment in the United States, introduces Alignment Geometry 1. Hunter Engineering has long held the reputation of being on the leading edge of the alignment industry, not only in the manufacturing of equipment, but in the training of service technicians throughout the country in the latest alignment methods. At Hunter, training has always been a key part of our customer support systems. We believe that training is the key to your business and ours. When you do the job right the first time for a customer, he'll come back to you again and again for that same excellent service. In addition, you'll be in a position to solve problems your competition can't. And this capability will help you enlarge your customer base. At Hunter, we have emphasized training from the day we introduced the first battery chargers, the first on-the-car wheel balancing equipment, and through our long line of innovative alignment and rack systems. That's why we now have several training centers in the United States and Canada. And that's why over 3,000 people go through Hunter training schools every year. The video you are now watching is the first in a new series of Hunter training videos and is designed to give you additional technical support. However, this video is not meant to replace the live training offered by Hunter training schools, but is offered as another facet of our ever-expanding training programs. During the next few minutes, you'll get an intensive yet easy-to-understand foundation in alignment geometry, which will be of great help to your understanding of automotive alignment. No, we're not going to give you a bunch of mathematical formulas to memorize, but a real-world explanation of the various angles that make up a vehicle's steering and suspension system. The geometry that makes today's vehicles and the tires perform as intended. And once you know these, you can't help but perform better alignments for your customers. This video is divided into 5 sections, each covering a vital element of automobile alignment. They are 1. Suspension systems, 2. Steering systems, 3. Camber, 4. Castor, and 5. Toe and related angles. We suggest you stop the tape at the end of each section and review. We furnished printed support material with the video, a workbook, and a booklet of test questions and answer sheets. As you view the tape, follow along in your workbook. When you've finished and reviewed each section, take the tests. Check your answers with the answer sheets. Then send the completed tests to Hunter together with your name and address, and we'll send you a Hunter certificate that you can frame and hang on your shop wall. Now let's move on to Section 1 and review the various suspension systems you'll find on vehicles today. This is a must because their role is to establish and maintain proper vehicle geometry. A car's suspension system is necessary not only for comfort, but to give the driver the control that's necessary for safe vehicle operation. It is used to support weight, absorb and dampen shock, help maintain tire contact, and provide proper wheel-to-wheel alignment. While there are many types of suspension designs in use, they can all be divided into two categories: non-independent and independent. Here's an example of a non-independent front suspension, the solid I-beam axle. The axle is of I-beam construction and is usually made of steel or sometimes aluminum. Attachment and support is provided by leaf springs, with the wheels located outboard on spindles that are attached to kingpins. The I-beam axle suspension system has a great load-carrying capability, so today it is primarily used on heavy trucks, buses, and off-road equipment. Manufacturers have used this system for years and will probably continue to do so because of its economical cost, simplicity, low maintenance, and heavy load capacity. However, the solid I-beam axle is not suitable for passenger cars because it doesn't provide independent movement of each wheel. As a result, in a light vehicle, such as a passenger car, the ride may be very uncomfortable and the handling difficult. To achieve the handling and ride characteristics necessary for passenger cars, independent front suspension systems were developed. These provide an isolated mounting for each wheel. The first and most widely used independent design that was developed was the short long arm, or SLA. An SLA suspension is made up of two control arms, an upper and a lower, a spindle or steering knuckle, which is attached to the control arms through ball joints, and coil springs or torsion bars. These may be used for support together with a shock absorber for dampening. Each control arm is attached to the frame through bushings and pivot shafts to provide an isolated mounting. The SLA suspension has been used by both domestic and import manufacturers on their passenger cars and light trucks for many years, and it is still used today on some rear-drive vehicles because of its superior ride quality and handling, qualities not available with the solid I-beam design. However, with the downsizing of the modern car and the advent of front-wheel drive, the SLA design is now viewed by some as too heavy, too complex, too costly to manufacture and maintain. It consumes too much space in the engine compartment, and many car manufacturers are finding it necessary to utilize an independent suspension system more conducive to the new small front-wheel drive package. Today, the most widely used suspension system is the McPherson strut, or some variation of the McPherson strut design. This suspension system has only one control arm, the lower, and the spring, shock, and spindle are one assembly. Because there is no upper control arm and fewer parts in general, a McPherson strut suspension is lighter, less costly to manufacture, and thus is viewed as more ideal for a front-wheel drive vehicle in a downsized package. But nothing is perfect, and there are some limitations to the McPherson strut. For instance, a large, heavy vehicle would require a strut assembly so large and tall, it wouldn't be practical to package it within desired body lines. Another limitation, with the McPherson strut system, you may give up some riding comfort. Unlike the SLA suspension, with McPherson struts, there is a much more direct path for road forces to reach the chassis or frame, and this can cause some reduction in ride quality. In recent years, a number of other hybrid strut suspension systems have been developed, and they've been somewhat successful in reducing road forces. But we won't take time to review them now because of their similarity to the conventional strut suspension just described. There's one more design I'd like to review, a very unique design in front suspensions. It's the twin I-beam front suspension system. This design has been used on many light trucks and vans since the 1960s. The twin I-beam front suspension was designed to incorporate the load capacity of the solid I-beam while maintaining the ride quality of independent suspension systems. The result? Two beams give the system strength and at the same time provide independent wheel travel. The axles may be forged or cast or in later designs made of stamped steel. Each axle is located by a radius arm and isolated from the chassis by a bushing at the small end of the axle and radius arm. The spindle or steering knuckle may be attached by either kingpins or, on some more current designs, ball joints. The twin I-beam suspension is a popular system. It's capable of providing both the necessary load capacity and ride quality. However, alignment adjustment without the right equipment or aftermarket kits can be difficult. Now let's take a look at the development in rear suspensions. Since most early passenger cars were rear drive, a non-independent rear suspension was chosen by most manufacturers because of its strength and simplicity. But simple or not, the rear suspension does affect the overall ride quality, handling characteristics, and tracking of a vehicle, and requires as much attention as the front. One of the most widely used non-independent rear suspensions was very similar in design to the I-beam front suspension. But instead of an I-beam axle, it employed a drive axle housing suspended and attached to the chassis with leaf springs. A variation on this same design replaces the leaf springs with control arms and coil springs. Another example of a non-independent rear suspension system is the beam axle. This design consists of a stamped beam that is suspended by coil springs and located by trailing arms and a link to control lateral movement. The beam axle suspension has become very popular among manufacturers of front-wheel drive vehicles because it is light and simple. Even though non-independent suspensions may be simple and cost-effective to produce, many manufacturers have incorporated independent rear suspension systems in their vehicles to take advantage of the superior ride quality and improved performance characteristics. One very popular design, commonly found on large luxury vehicles, is the trailing arm suspension system. This system is made up of a lower trailing arm and spindle assembly and is suspended by coil springs. Each trailing arm is attached to the chassis through bushings along a line perpendicular to the center line of the vehicle. However, as in the case of the SLA suspension system, the trailing arm design has been replaced in some applications by the McPherson strut suspension. As you can see, the McPherson strut rear suspension system is almost identical in design to a front McPherson strut system. That completes Section 1, Suspension Systems. I suggest you turn the VCR off now and review what you've learned using the workbook. When you're ready, turn the VCR on again. I'll wait right here. Welcome back. Now it's time for Section 2, Steering Systems. And I'd like to discuss two common steering systems. One has been in production for many years, and the other is a much more recent system. The first is the conventional steering system, a linkage system used by most auto manufacturers until a few years ago. This design was originally developed to accommodate independent front suspension. It's sometimes called parallelogram linkage because if lines were drawn through the pivot points, the lines would be parallel. The components that make up this linkage are two tie rod assemblies, two steering arms, a center link, an idler arm, and a pitman arm which is attached to the steering gear. Again, as with the SLA suspension, some of today's auto manufacturers view the conventional linkage system as too heavy, too complex, and too costly to manufacture and maintain. Many of these manufacturers have chosen to replace the conventional linkage system in both passenger car and light truck applications with rack and pinion. Some of the advantages a rack and pinion system offers are fewer parts, less weight, simplicity of design, and space savings. Notice that the steering gear is now part of the linkage assembly, and many components that were used on the conventional linkage system have been eliminated. Probably the only major disadvantage with this design is its sensitivity to road forces and its inability to isolate them as effectively as the conventional system. This concludes our discussion of suspension and steering systems. It was not our intent to give you a detailed suspension and steering course in this video. The purpose of this discussion was to give you a general understanding of the changes in suspension and steering development so you'll be better prepared to service the cars of today. In-depth diagnostic information related to specific steering and suspension systems will be discussed in our second training video, Alignment Geometry 2. Let's take a break now so you can review steering systems. When we return, we'll be discussing alignment geometry and Section 3 of this video, Camber. Welcome back. This is Section 3. For simplicity, we'll concern ourselves with three primary angles. They are camber, castor, and toe. We'll begin with camber. Camber may be defined as the angle formed by the inward or outward tilt of the wheel as compared to vertical. Camber is expressed in degrees and is displayed as such by most alignment equipment. There are three possible camber positions: 0, positive, and negative. Camber is considered positive when the wheel is tilted outboard at the top, and negative when the wheel is tilted inboard at the top. 0 camber exists when the wheel is vertical or straight up and down. Most manufacturers specify a positive front camber setting as preferred. The reason is that positive front wheel camber helps isolate road forces and maintain directional or straight-ahead driving stability. But because of the wide variety of makes and models of vehicles in production, you cannot assume that one camber setting will work for all. You must always refer to the manufacturer's specified camber for each vehicle you align. If you don't, the result will usually be unacceptable to your customer. In this first example, we have a front wheel camber spec for a current production rear drive vehicle. You can assume this spec is positive because there is no minus sign, and it's to be applied to both the left and right front wheels as there is no individual wheel indication. In this next example, you'll notice we do have individual left and right wheel specifications. In years past, this was common practice among many manufacturers and was used to compensate for road crown. But today, when individual left and right camber is specified, it usually has nothing to do with road crown, but is used instead to enhance directional stability. This is an example of a front camber spec for a current production front drive vehicle. From these examples, you can see the variations in specified camber from manufacturer to manufacturer. So whenever you're in doubt, be sure to refer to the manufacturer's specifications for both diagnostic and adjustment purposes. If camber is excessively above or below the factory specified tolerance, two problems may result: a tire wear problem or a handling problem, or both. If camber is exaggerated in a positive direction, it will cause an increased amount of scuffing on the outside edge of the tread. If you were to continue to operate a vehicle at this exaggerated setting, a noticeable shoulder wear pattern on the outside of the tire may develop. If camber is exaggerated in a negative direction, just the opposite will occur. The result will be increased scuffing on the inside of the tire that may develop into a shoulder wear pattern on the inside of the tread surface. You must also take into consideration any difference in camber side to side. In other words, any difference between one wheel and the other. Since a cambered wheel does not want to roll straight ahead, it's important that those rolling forces be balanced on each side of the vehicle. In this illustration, you'll notice that the wheel wants to roll away from the center of the vehicle all the time. That's because the wheel is cambered in a positive direction. Here we have a wheel cambered in a negative direction. This will cause the wheel to want to roll inboard towards the center of the vehicle. In order to balance these forces, most manufacturers will specify the same front camber angle for each side. With camber set to the same specification on each side, then theoretically, camber should help the vehicle maintain a straight-ahead course on a flat level surface. If we have a vehicle with a camber setting on the left front wheel of 1 1/2 degrees positive, and on the right front wheel a setting of 0, this vehicle may have a tendency to pull or lead to the left because of the 1 1/2 degree side-to-side camber difference. The left front wheel at positive camber is trying to roll left all the time, therefore leading the vehicle to the left. As a general rule of thumb, camber should not vary side to side by more than 1/2 degree unless specified otherwise. Now let's take a look at rear wheel camber. With the vehicles that are currently in production, you can no longer afford to ignore the rear wheels, and that certainly includes rear camber. But one major point in our favor is that almost everything we understand about front wheel camber holds true for rear wheel camber. There are some exceptions, but let's look at the similarities first. A positive position is still out at the top. Negative is still in at the top. And of course, 0 camber is when the wheel is vertical or straight up and down. If exaggerated, rear camber may generate the same inside or outside shoulder wear on the rear tires as we have seen occur at the front. But as you'll notice, rear camber specifications are not predominantly positive. Many manufacturers specify near zero or slightly negative rear camber because they feel this helps maneuverability. Also, it is very difficult to trace a pull or lead to a side-to-side difference in rear camber, since the rear wheels are not free to steer. As you can see, your understanding of camber is applicable regardless of which corner of the vehicle you're looking at. And on vehicles with adjustable rear camber, adjusting the rear to factory specs can be as important as adjusting the front wheels to factory specs. It will avoid irregular tire wear and other problems. So let's review what we've learned about camber. First, camber may be defined as the angle formed by the inward or outward tilt of the wheel as compared to vertical. Camber is considered positive when the wheel is tilted outboard and is considered negative when the wheel is tilted inboard. Excessive positive camber may cause outside shoulder wear on the tire. Excessive negative camber may cause inside shoulder wear. A large difference in front camber side to side may cause a pull or lead, and the vehicle will have a tendency to lead to the side with the more positive setting. This completes our discussion of camber. To make sure you understand all aspects of camber, you may want to go back and view this section again, or you may want to turn the VCR off and review the workbook. Either way, I'll wait right here until you're ready to start again. You're now ready to begin Section 4, Castor. Castor may be defined as the angle formed by the forward or rearward tilt of the steering axis as compared to vertical. The steering axis is an imaginary line drawn through the upper and lower steering knuckle pivots. Castor is expressed and displayed in degrees by most alignment systems. Castor is considered positive when the top of the steering axis is tilted to the rear, and negative when the steering axis is tilted forward. Castor is zero if the steering axis is vertical or straight up and down. Most manufacturers prefer and specify a positive Castor angle in order to improve directional stability and returnability. As you will recall from our discussion of camber, directional or straight-ahead driving stability is the vehicle's ability to maintain a directed course. Returnability simply describes the characteristic which forces the front wheels back towards straight ahead after they are turned. As with camber, you cannot assume that one Castor setting will work for all vehicles, so always refer to the manufacturer's specified Castor setting for each vehicle you align. Let's take a brief look at the variations in specified Castor. In this first example, we have a Castor specification for a current production rear drive vehicle. This spec is assumed to be positive because there is no minus sign, and it's meant to be applied to both the left and right-hand sides as there are no individual wheel indications. This is an example of a Castor specification for a current production front drive vehicle. You'll notice that this spec is also positive and should be applied to both sides. Although we prefer the effects of positive Castor, if taken to an extreme, it can cause problems. A vehicle with Castor exaggerated in a positive direction may exhibit any or all of the following symptoms: hard steering, excessive road shock, or front wheel shimmy. Excessive negative Castor should also be avoided. As Castor is moved further negative, the characteristics provided by positive Castor are severely reduced to the point in some cases where the vehicle may wander. You must also take into consideration any difference in Castor side to side. If there is a large difference in Castor between the two front wheels, this may cause the front wheels to steer, inducing a pull or lead. And just like camber, you can predict the direction of the lead. In most cases, the vehicle will steer towards the side with the least amount of Castor. If, for example, you were to have 5 degrees of Castor on the left front and 2 degrees on the right front, the wheels may want to steer to the right all the time. This could cause the vehicle to lead or pull on the highway and generate a customer complaint. In order to avoid a Castor pull, Most manufacturers will specify the same Castor angle for each side. Castor, if set evenly, will theoretically help the vehicle maintain a straight-ahead course. As a general rule of thumb, Castor should not vary side to side by more than 1/2 degree, unless specified otherwise. Now let's review what we've learned about Castor. Castor may be defined as the angle formed by the forward and rearward tilt of the steering axis as compared to vertical. Castor is considered positive when the top of the steering axis is tilted rearward. Castor is considered negative when the steering axis is tilted forward. Excessive positive Castor may cause hard steering, road shock, or front wheel shimmy. Excessive negative Castor may cause a reduction in directional stability. A large difference in Castor side to side may cause a pull or lead, and the vehicle would pull towards the side with the least amount of Castor. This completes our discussion of Castor. If some areas are still unclear to you, go back and view this section again, or turn off the VCR and review this section of your workbook. This is Section 5, Toe and Related Angles. First, let's discuss toe. Toe may be defined as the difference in distance measured across the front and across the rear of the tires. Toe in is when the front of the tires are closer together than the rear of the tires. Toe out is when the front of the tires are further apart than the rear of the tires. When the wheels are parallel, toe is considered to be 0. Individual toe may be described as the difference in distance of the front and rear of one tire in reference to a line that is drawn through the center of the car. Unlike Camber and Castor, it has become difficult to generalize, let alone predict, how toe may be specified by any manufacturer. In the past, almost all rear-drive vehicles were specified as toe in for the front wheels, and most front-drive vehicles were specified toe out. The following examples will illustrate the vast differences in how front-wheel toe may be specified. In this first example, we have a front toe specification for a current production rear-drive vehicle. This spec is assumed to be toe in, or positive toe, because there is no minus sign. Also, all toe specifications are total toe. Therefore, half would be applied to each front wheel. This is an example of a front toe specification for a current production front drive vehicle. This spec is understood to be toe out, or negative toe, because of the minus sign. Again, half of this spec would be applied to each front wheel. Here's another example of a current production front drive vehicle, but the front toe specification is toe in, or positive toe. Regardless of how toe is specified, toe in, toe out, or 0, all manufacturers are attempting to achieve the same general goal, a 0 or near 0 toe during most driving conditions. This is to minimize the amount of scuffing across the tread surface of the tires to help prolong tread life. If toe is exaggerated positive, or toe in, there may be increased scuffing on the outside of the tires. This can generate shoulder wear on the outside of the tires and cause a darting effect in some cases. If toe is exaggerated in a negative direction, or toe out, there may also be scuffing, but now on the inside of the tires. Shoulder wear may soon develop on the inside of the tires and cause, in some cases, wander. Another tire wear pattern that is typically associated with toe errors is a sawtooth or feather edge. This is much more common with the old bias and bias belted tires than radials. In this illustration, you can see the typical feather edge wear caused by excessive toe. Just as with Camber, rear toe has become as important a consideration as front toe. And again, almost everything we understand about front toe holds true for the rear wheels. The definition of rear toe is the same. Toe in, or positive toe, is the same. Toe out, or negative toe, is the same. And individual rear toe, by definition, is also identical. Specifications for rear toe, however, are generally positive or toe in. This is illustrated in the following examples. Exaggerated rear toe may generate very similar tire wear patterns, but But in addition to the typical shoulder wear characteristics, you may see this, a wear pattern referred to as diagonal wipe. Diagonal wipe has become a very common abnormal tire wear pattern on the rear tires of a front-drive vehicle. You will usually find that rear toe is out of adjustment when this wear pattern is present. So as you can see, your understanding of toe and the effects of toe apply to all corners of the vehicle. And rear toe is now just as important a consideration as front. To further your understanding of toe geometry, you will also need to understand the related angles. These are called thrust line, geometric center line, thrust angle, and center steering. This information will help you understand how to achieve a more accurate front wheel alignment and understand the simplicity of four-wheel alignment. Thrust line may be defined as a line bisecting rear toe, or more simply stated, the direction the rear wheels are pointed. If the rear wheels are pointed to the right, then thrust line is to the right. If the rear wheels are pointed to the left, then thrust line is to the left. However, rear individual toe is seldom equal. Even when this is the case, thrust line is the bisector of toe. Since thrust line of the rear wheels dictates the position of the front wheels when driving straight ahead, this would be the most accurate reference from which to measure and adjust front wheel alignment. If thrust line is ignored, which is what was done in the old two-wheel front end alignment, there can be no guarantee that the alignment will be accurate. This may be one of the primary causes of a crooked steering wheel after performing a two-wheel front end alignment. Obviously, using a thrust line reference is preferred on any vehicle with non-adjustable rear wheels. You should never assume that the alignment of the rear wheels is correct. Thrust line also allows us to compute thrust angle. But first, a center line reference must be established. We refer to this reference as a geometric center line, which is simply a line drawn through the midpoint of both the front and rear axles. By comparing thrust line to the geometric center line, thrust angle may be computed. Thrust angle is expressed and displayed in degrees. If the rear wheels are pointed to the right, then thrust angle is defined as positive. If the rear wheels are pointed to the left, then thrust angle is defined as negative. Knowing the amount and direction of rear wheel thrust angle is important, not only as a diagnostic tool, but also in making rear wheel alignment adjustments. When performing a four-wheel alignment and adjusting rear toe to equal, then thrust line becomes parallel with the geometric center line and thrust angle is reduced to zero. Earlier, we referred briefly to steering wheel position or center line steering. Because of the importance of steering wheel position to your customer, it's important for you to understand the geometry necessary to achieve this. First, the steering wheel must be locked in a level position when front toe is adjusted. Then adjust individual toe to be equal and half of your specification on each wheel. When we say front toe is equal, that means that the front wheels are at equal individual toe angles in respect to rear wheel thrust line. Remember, when any four-wheel vehicle is put in motion, the front wheels will automatically assume a direction parallel to the rear wheels. The only way to simulate this on a rack is to measure and adjust the front wheels in respect to rear wheel thrust. Okay, now let's review what we've learned about toe and related geometry. Toe may be defined as the difference in the distance measured across the front and across the rear of the tires. Toe in is when the front of the tires are closer together than the rear of the tires. This is referred to as positive toe. Toe out is when the front of the tires are further apart than the rear of the tires. This is referred to as negative toe. Individual toe is the difference in distance at the front and rear of one tire in reference to a center line. All of these definitions apply to the rear wheels also. Excessive toe in may cause outside shoulder wear and in some cases darting. Excessive toe out may cause inside shoulder wear and in some cases wandering. Thrust line may be defined as a line bisecting rear toe, or simply the direction the rear wheels are pointed. A geometric center line is a line drawn through the midpoint of both the front and rear axles. Thrust angle is the angle formed by thrust line and the geometric center line. Centerline steering refers to a level steering wheel while the vehicle is traveling straight ahead. This completes our discussion of toe and related geometry. We suggest you go back and view this section again if some parts are still unclear. I'll wait right here. We hope this presentation has helped give you a better understanding of vehicle geometry and will result in more satisfied customers for you. We invite you to attend the Hunter Training Facility in Bridgeton or any one of our satellite training centers if you feel that live training will better suit your needs. You can also contact one of our Hunter ASE certified service representatives if you want on-site training. The next in this series of technical training videos is Alignment Geometry 2. Your Hunter representative can help you obtain a copy. In addition, we have produced 2 merchandising videos you will be interested in. They are How to Sell Four-Wheel Alignment and Total Four-Wheel Alignment Passenger Cars. This concludes Alignment Geometry 1. We at Hunter Engineering Company sincerely hope the information given you here will help you improve your skills as an alignment technician and increase your profitability. Thank you.